Hi all. In this video I want to do a demo of how to use this new concrete module in Standard Solver. So I created this module but I never did any tutorial yet, so I thought I will try to do one tutorial solving a problem in a textbook and see whether we can get a similar results. One thing to remember is, the textbook formula, they are a conservative solution, so FE may be not an exact match, but it should be close enough. So let's try one of the problem in this textbook of analyzing this concrete beam and finding its ultimate bending capacity. So to use Standard Solver, go to standardsolver.com and go to concrete module. You will reach here. Okay, let's clear everything. What we have here, then let's create the beam. So what we do, let's create the material we want to use. So the material in the problem is a concrete with a compressive strength of 35 Newton per millimeter square and a reinforcement yield strength of 500 Newton per millimeter square. So let's create these materials first. So let's create concrete. So we call it concrete, then so this is not very great. You need to create it in concrete. So let's see concrete 35. So we need to enter concrete density. I don't exactly know what's the general density. Let's put some value because we are not worried about creating, checking the weight of the section. So just some random value. Tensile strength, let's put 0. Then color of this section, let's put it as maybe some yellow. Then we need to provide the service profile and ultimate stress strain profile for concrete. So let's create it at profile. So let's create concrete service profile, then linear. Let's create with a linear. So we need to enter elastic modulus of concrete. I don't know whether this is used in the actual calculations. So let's enter 30 megapascal. Then ultimate strain, just leave it at 1. I think it will affect for the textbook problem we are trying to do. Then let's enter concrete ultimate profile. Then so view the problem, use a rectangular stress block. So let's use rectangular stress block. Then the compressive strength we are using is 35 megapascal. Then alpha and gamma factors, generally the factors we are using are 0.85 for alpha and 1.5 for gamma. And the ultimate strain, you can put like a typical ultimate strain. I don't know whether that will also affect the analysis. So okay, now let's apply these profiles. So we create the concrete. Now let's create the material for the steel bar. So let's call it steel bar 500 yield strength. So we want to assign steel bar. So density is 7850. Okay, no, we need to create the stress strain profile. We need to pick a color for it. Let's create color, select pink. I don't think for bar it doesn't matter, but yeah, let's put true. Doesn't matter. There is no pre-stress, so we need to create the stress strain profiles for steel. So steel bar profile, then select say elastic plastic profile we can do. So the yield strength is 500. Then the elastic modulus of typical steel is 200 gigapascal, so 200 times 1000 megapascal. Then the fracture strain is so if we have say 500 yield strength steel, we divide it by 200 megapascal, we will get 0.0025. So yield strength of steel, we want to apply some safety factors gamma s, so we want to divide it by 1.15, so it is 434.782. So we get the steel, then okay, let's apply this steel bar profile. So we got the material covered. Let's create geometry. Okay, we will do geometry, the beam. We want to use the rectangular section. So the section is 550 deep and 250 wide. So add that geometry. So we got this section and assign concrete as its material. We don't want to do anything else. Then let's apply the reinforcement. We can use rectangular bar array, so it will be a kind of like an array of bars. So that okay, area of the bar. So area of the bar, we are saying 3 bars with a diameter of 32 mm. So the area of the bar is pi by 4 times 32 square. Till Q, I'm just using calculator. Calculate it. So area of single bar is 804.2477 millimeter. So material, we will select concrete. Then we want 3 bars at a spacing of, so 3 bars are spaced like on a 250 wide section. So let's divide it by 3. 3 divided by 3 will be 833. So let's put 833 as spacing. Yeah, so we go. Then the first will be sorry, I had a slight recording issue, but let's continue. So we have, okay, let's move the reinforcement into correct location. So the reinforcement is 50 above from the bottom, so let's enter y anchor position as 50. Then x anchor, let's move it inwards by half of this value, so 41.665, so they are nicely centered. Also I want to adjust one value. Yeah, this one. Yeah, we want to, I think previously I entered a slightly 43.87, something like that. The textbook work with rounded off numbers, so we want to get close to the textbook value, so that's why I just adjusted it. Then I think now we got everything we want. Let's run the analysis. So this everything's 0. You can enter minus pi to do a hogging moment analysis, but we want sagging analysis on this section, so we keep it 0. Let's run it, and sorry, we didn't get the exact value, but I think this is 804. I think this reinforcement area is rounded off, so let's enter pi 432 here square. It is actually 804.247. So we'll get more close to the textbook value. So we can see we got a 427 kilonewton meter if you convert it into the right unit, and the textbook is 414. So we are 10 kilonewton off, but we are close enough. So yeah, this is an example of analyzing a concrete beam. Give it a try yourself. See if I missed anything, let me know. I haven't went through this concrete textbook for a while. Nowadays I don't work with concrete that much, but to give yourself a try and see whether you can get similar value to other textbook problems. But yeah, so we are getting a close enough match, but if we never match the exact formulas in textbook. But yeah, so yeah, thanks for listening. Give it a try. Hope you find good use of this module and help you design lots of concrete sections. I'll come with more tutorials in the future. But yeah, thanks for listening. Thank you. Bye.